Okay, so we'll just do a quick, not really review, summary of what we did last day, just to kind of get warmed up here. So we talked about the properties of the nth root, right? Things like we can't take the even root of a negative number, right? We can take the odd root. So for example, the third root of a negative number, that's allowed. What are some other properties? We can rewrite the root as an exponent with a fraction, right? So, or a fraction in the exponent. That's a quick trick. We can combine roots as long as they're the same and we're multiplying or dividing. And same thing, we can split them up across. So we talked about all those different properties of the nth root. We also talked about rationalizing the denominator. Rationalizing the denominator. That's where we did a little bit of work to make sure that there's no root in the denominator, right? So standard form is also what it's called, means that there's no root in the denominator, which meant we had to put it up in the numerator, right? So we had to do a little bit of work. We multiplied by 1, some convenient value of 1 to get that root from the denominator up to the numerator. Then we went on to talk about polynomials. Right? Then we started section 1.3, where we started talking about polynomials, different terms around polynomials, right? The polynomial of degree 4 means that the highest power of the variable, typically x, is 4. Just things like that. We talked about, well, each little chunk of stuff in the polynomial is called a term. And all that fun stuff, and that we usually list the polynomials, we list the terms in order of decreasing powers, right? So starting with our degree, kind of showing off the degree of the polynomial. And then we talked about adding or subtracting, adding and subtracting polynomials. That was all fine, right? You probably need to simplify by collecting like terms and then simplifying those coefficients. But besides that, adding and subtracting polynomials is not bad. Multiplying polynomials we saw, and it's kind of where we left off a little bit. Multiplying, if we have 2 binomials, right, so 2 polynomials with only 2 terms each, then we use FOIL, but in general we have to distribute each of the terms across, across both the polynomials. So we ended up talking about the special product formulas. And I kind of gave you a heads up that the special product formulas in reverse are going to be way more useful than just the special product formulas. I find it's easier to just do it, right? And we saw the example of where we expanded, right, a minus b to the 3 is a to the 3 minus 3a squared b minus 3ab squared minus b to the 3, right? So that's the one we did last day. That's a special product formula. But like I said, I find that it's just easier to write this out and then expand it myself instead of memorizing all these things. But like I said, recognizing the shape of this or the pattern of this is going to be useful for when we start factoring today. And so factoring is, I I find factoring a little bit trickier than expanding, right? Expanding, we're just making it bigger, bigger, bigger. And factoring, we're trying to bring it down to size, right? And then one thing to keep in mind, right? A minus b to the 3 is a minus b times a minus b times a minus b, right? So what we did was we had to take this a, and then we expanded the first chunk, and then we expanded it onto the second chunk, or the third chunk, I guess. Chunk. Okay. So that's all from last day. I haven't seen any questions, but if you do have a question, just I'm getting better at keeping an eye on the chat. Actually, I feel like I'm really good at it now, but who knows? So just if you have a question, you can throw it in the chat. We'll see what we can do. I know it takes a little bit to type it up, but if you want to, you can unmute your microphone too. That way I'll stop in my tracks. Okay. So today we're gonna keep talking about just kind of expanding and then getting into factoring. And then what do we do? And then what? Yeah, factoring. And then if there's time, we'll start 1.4. I suspect that there isn't, and that's actually right on track with where I usually am. So nothing crazy going on. Don't worry, 1.3 is a really large section. So let's see here. Special product formulas continues. Product formulas continued. So where do I have these little tidbits? Oh, I had to move them over here. Okay. So let's bring this whole kit and caboodle into our notes so we can write about them. All right. So the reason we have these special product formulas, and hopefully you have them kind of from last day, or I can go grab them too. But one thing, like I said, is that being able to recognize a pattern like this, right? This kind of a coefficient of 1 something to the power of 3, so it's not necessarily a nice thing to the power of 3, but if we can kind of imagine 1 thing to the power of 3, and then minus a coefficient of 3, and then something, that same thing squared, something up times something else, minus a coefficient of 3 times that first thing times that second thing squared minus that second thing cubed. Or if we have something easier to look at, right? If we can convince ourselves that we have, and I will go grab it, or maybe I'll just do it on here, right? If we can convince ourselves that, okay, I have something that looks like a squared plus 2ab plus b squared, right? Even if it's not a nice a or b, if I can kind of see something and convince myself, okay, well, that's going to be my a, and then whatever I'm seeing is going to be my b. So for example, if I have something like x squared plus y to the 3 squared, okay, so this is kind of the easy way, and then later on we'll be factoring this stuff. which is going the other way, then I can say, okay, well then if I have something squared, I've got one term and a second term, right? So this is going to be my A and this is going to be my B. So then I just take that x squared as my A, and then I can use this special product formula and just write it out. It's going to be harder when we have, now I'm trying to cover up, but I'm just doing it on my screen and it doesn't help very much, right? It's going to be harder later on when we don't have this, but we do have this, and we want to get it back to something like this. So when we're moving from here, from the right-hand side to the left-hand side, then we're factoring. If we're moving from the left-hand side to the right-hand side, then we're expanding, right? So expanding is a little bit simpler, I think. But if you like factoring, then that's great. That's really good, but it can be a little bit tricky, right? So in this case, you're going to go through and read this and say, oh, okay, well, I've got a square here, and I've got two terms inside. So my x squared is going to be my A, and my y to the 3 is going to be my B. So then if I use that special product formula, then I can just rewrite this as A squared. Well, that's going to be x squared squared plus 2ab, so 2x squared y to the 3 plus b squared, which is y to the 3 squared. So a lot of the exercises that you'll see might be special products, right? But like I said, for me, right, if we just do x squared plus y to the 3 squared, or we can expand, I'll say manually. Right? Because this is the same as x squared plus y to the 3 times x squared plus y to the 3. Right? It's going to get a little messy because I have to go from this x squared and I have to expand it all out. But just as a little warm up, let's just go through and do this, and we'll see that we end up at the same result that we would have with the special product formulas. So I have x squared times x squared. So now I'm going to go a little bit faster. I'm still writing out extra steps. So x squared times x squared is, I could have just skipped to x to the 4th, right? 2 plus 2 is 4. But x squared times x squared plus x squared y to the 3 plus y to the 3 x squared plus y to the 3 times y to the 3. X squared times x squared, x to the 4th. If I rearrange x squared y cubed x squared, they're the same, right? So I've actually got 2x squared y to the 3 plus 2x squared y to the 3. Oops. Make that look like a 3. Y to the 3 times y to the 3 is y to the 3 plus 3, y to the 6. Which is what we have here, right? If we bring in this square, so we've got x squared squared, right? We know from the properties of exponents, that's x to the 4th, and then 2x squared y cubed just stays as it is, and then y to the 3 squared, same thing, y to the 3 times 2 is y to the 6, so they're equivalent. So just keep in mind, so expanding, you don't really need those special product formulas, but it is good for factoring. Okay. So, let's get into factoring then. So there are some exercises here that you can give a try, but because it's just using the special product formulas, I'm gonna just skip it because, I mean, I'm happy to go through and do some of these and expand it manually, because I think that's gonna be way more useful, but it wants you to do it with the special products, which are these guys here. Oops. Okay. Oh yeah. So for factoring, let's see. Let's steal this into our notes. So if we're factoring, okay, it means that we're going from something like this, right? So from essentially a polynomial to smaller powers of x. And so it means that we're kind of spreading it out, or making it more compact, right? And then expanding is when you go from here and you kind of expand it to a big polynomial. And so usually the reason we want to factor is to be able to cancel terms. Okay, so that's usually why we want to factor. Sometimes it's to simplify things. It just kind of depends on what you're doing. But a lot of the time it's to be able to cancel stuff. So we usually factor to be able to easily cancel a term or terms. So if we have a look at the example here, right? If I've got x squared minus 4 divided by x minus 2, okay, one thing that I want to make very clear is that I can't just take this negative 2 and cancel with a 4. That's not allowed. That's illegal math. Okay, so what we can do, though, is we can rewrite the x squared minus 4. We can expand it, or sorry, we can factor it into two parts. So x minus 2 times x plus 2. So now divided by x minus 2. So now I am allowed to cancel this because it's the x minus 2 is multiplying all of these terms. That's the only time that I'm allowed to cancel. So now I can cancel this with this. So the answer is going to be x plus 2. Let's do an example. I'll go grab one. So the easiest way to do it is to just pull out a common factor. So a common factor is a multiple of each term inside your polynomial. And then you kind of extract it. So you pull it out and you multiply it on the outside. So up here, x squared minus 4, well, that looks like a special product, right? So if you go back to your special products in reverse, then you can rewrite it as the special product. But also you can pull out an x minus 2 and end up with x plus 2. But that's not obvious, right? So, but sometimes it will be obvious. So let's do 68, nice and big. 68. Negative 7x to the 4th y squared plus 14x y to the 3 plus 21x y to the 4th. And we want to factor out common factors. So first thing I'm going to do is I'm just going to scan and I'm going to check out my coefficients first. So my coefficients are negative 7, 14, and 21. All of these seem to be multiples of 7, right? I can extract a 7 from each of these. 7 takes away this whole thing. 14 divided by 7 puts me at 2, and then 21 divided by 7 puts me at 3. Let's see here. Coefficients have a common factor of 7. Okay. So how about if we look at so the x's, right? So each of these terms have an x, so surely I'll be able to pull something out, right? I've got x to the 4th, x, and x. So my smallest power of x is just x to the 1, right? And so that's all I'll be able to extract, right? So just like with the coefficients, 7 was my smallest number, so that's the largest I could possibly pull out there. So because x to the 1 is my smallest power of x, then that's all I can pull out. If there was a term with no x, so say this last term just was 21y to the 4th, then we wouldn't be able to pull out a common x, right? Because we have to pull it from each of these terms. So here, x has a common factor of just x. Nick's got it. But let's just talk about what's going on. So y squared, so same thing, we look at the y's now, and I want to make sure that there is a y term in each of, or a y value in each of these terms. And so I've got y to the power of 2, y to the power of 3, and y to the power of 4. So y to the power of 2, that's my smallest possible power of y. And so I'll be able to extract that from y to the 3 and y to the 4. Remember, so y to the 3 you can rewrite as y to the power of 2 times y to the power of 1 because of how the exponents behave. So we'll be able to pull that out. Y has a common factor of y squared. So what I'm going to do is I'm going to pull out, so usually this negative here, I would just leave the negative and only pull out the positive 7 and then deal with that negative later. So this becomes 7. So now I'm going to put all my common factors together. So 7xy squared. And then in brackets, I'm going to leave everything, or write out everything that's left, right? And so I've got negative, I need to have negative 7. So I've got a negative remaining here. I've pulled out one x, but I need x to the 4th here. So I'm going to be left with x to the 3. And then I've pulled out the entire y squared, so that's moved out to the front. Moving on to the next one. Oops. So from 14, I've pulled out 7, right? We're divided by 7. And so I need to multiply 14 by 2. So plus 2. I pulled out one x and I've pulled out two y's, so I need two y. From 21 divided by 7 puts me at 3. So plus 3. I pulled out that x, and then y to the 4, I pulled out 2 of those 4. So y squared. Okay. So here, right, a good idea is just to, especially if you're not sure about your factoring, a good idea is just to go and expand it out and just make sure that you end up with the same answer that you started with, right? So we should, when we expand this, we should end up at the same polynomial that we started with. Okay, so I will say that as a note here, when factoring, it is always a good idea to expand out your factoring. I know I said factoring twice. To make sure you get back to where you started. To make sure you get back to where you started. So if I have 7xy squared negative x to the 3 plus 2y plus 3y squared, if I'm expanding this thing, then I've got 7xy squared times negative x to the 3 puts me at negative 7x to the 4y squared, right? Going a little bit faster. And then on to the next term, right? 7xy squared times 2y. So plus 14xy to the 3 plus, and then same thing, 7xy squared times 3y squared puts me at 21, xy to the 4th, which is hopefully where I wanted to go from, or go to. I can just barely have it on the same page. There we go. Hold it. Negative 7x to the 4th, y squared, 14xy to the 3, 21xy to the 4th. I'll just put a little smiley. Right. So just always go through, and if you're you know, not 100% confident in your factoring, then just go through and just check it. Okay. All right. The next part in your notes goes on to do the same thing with trinomials. That's more good to know than, so we're not going to spend any time on it, but if you want to kind of exercise the mind, then sure, go through it. But so this stuff is good to know, but I'm not going to test you on it or anything. But not tested. Okay. There are going to be some kind of easier trinomials that we'll be able to factor out, but we'll wait until I think 1.5 to deal with that. Quadratics. a little bit easier. Okay. So we'll table that for now and go to these special factoring formulas. You'll notice that this is basically the exact same thing that we were seeing with the special products, just in reverse, and that's what I was saying. So here, I will say that these special factoring formulas, so these will be useful to know and recognize, right? So recognize the patterns, especially if you can say, oh, okay, well, I've got something that looks like a to the 3 minus b to the 3, whatever a is and whatever b is, then you'll be able to rewrite it as something, as a difference of cubes, for example, like this, which might help you kind of cancel stuff and simplify things. Okay? So I will say that these will be useful to know and recognize. Mostly recognize, right? So especially if you see something that's like a squared plus 2ab plus b squared, just like we were talking about, easy enough to expand from a plus b squared to get to this expanded version. But if you're trying to kind of accordion things up, right, that's factoring. So then a squared plus 2ab plus b squared, if you recognize that pattern, then you can say, okay, well, I can summarize that as a plus b squared, and we call these perfect squares, right? A minus b squared or a plus b squared, and get those in reverse. So, do I have, let's do a quick, let's see here. Which one should we do? If we have to factor something like, and some of these are a little bit trickier than what we want. Let's do, something a little bit easier. Easier. Only because I don't want you to worry about too much. 78. If we have something like x plus 3 squared minus 4, okay, it's not obvious right away, right? But, well, this one's kind of the most obvious out of a lot of these. But x plus 3 you can treat as one thing. So something squared minus 4, but 4 is 2 squared, right? So we can rewrite this 4 as a squared. So this is x plus 3 squared minus 2 squared. And now all of a sudden, I've got a equals x plus 3 and b equals 2, which means I can rewrite this as a minus b, or a squared minus b squared. So if I look here, and I've got a squared minus b squared, the first one here, I can rewrite that as a difference of squares, so a minus b times a plus b. So is a minus b times a plus b. In terms of if a is x plus 3 and if b is 2, right, I can rewrite these. And I can say, okay, well then x plus 3 squared minus 2 squared is the same as x plus 3 as one thing minus 2 times x plus 3, treating it as one thing, that's important, plus 2. And we can simplify this, x plus 3 minus 2, x plus 1. And x plus 3 plus 2, x plus 5. This is going to be a little bit trickier to check, right? But just as an exercise, let's go through and just make sure that we can get back to where we started, right? Because that's the whole idea. I want to have this equivalent to this, right? The factored version. So check our factoring. So we want to make sure that x plus 1 times x plus 5 does it equal, so I just do a little equal sign with a question mark over top, does it equal x plus 3 squared minus 4? And at first glance, no, not necessarily, right? But what I'm going to do is I'm going to expand this out and then see kind of if I can manipulate it to look the same. All right, if I can't, then I did something wrong. So I've got x squared plus 5x plus x plus 5. Moving a little bit quicker. Okay. Which is going to be x squared plus 6x plus 5. Okay. This does not look like the right-hand side quite yet, but what I can do is, well, one thing I can do is I can pull out a common factor of x plus 3 from here, which it looks like I can do. But instead, I'm going to expand this out just to make sure that I get to the same values. So does it equal x plus 3 times x plus 3 minus 4? X times x is x squared, x plus 3x plus 3x plus 9 minus 4. So it does equal x squared plus 6x plus 5. Woohoo! So this confirms that our factoring was correct. This confirms that our factoring, that our factoring was correct. Which means that x plus 3 squared minus 4 does equal x plus 1 times x plus 5. Is that what I, yeah. So we need to be really flexible and just kind of expanding is going to play a huge role, but like I said, factoring kind of involves expanding in a way because I always like to check things, and so then you have to expand things. Okay. Later on, you might hear someone or people, you might hear people talking about a perfect square. Usually if you go on into calculus, for example, then you might hear about perfect squares. Perfect squares are just a trinomial where you have either 2ab or minus 2ab squished between a squared plus b squared. So up above here, these two are perfect squares, which we already talked about, right? So a plus b squared and a minus b squared, those are perfect squares, and they have the same sort of pattern. Okay? So I'll put it in our notes, but not really going to do anything about it. Just being able to recognize those perfect squares is good. Perfect square, if the middle term is 2 plus 2ab or negative 2ab, and then okay, this I want to do. Factoring with fractional exponents. Here, we're going to get to work out our exponents again, always. So if we have fractional exponents, something like x to the power of 5 over 2 minus x to the 1/2, we can factor these expressions still, okay? So what we do is we manipulate these exponents, which we can do, right? We can break them up and then we'll be able to factor out kind of the lowest power of each. So let's have a look at which one? Oof. Should we just do 96? Get into the groove. After that, everything will seem a little bit simpler, right? So let's see here. So like it explains here, begin by factoring out the lowest power of each common factor, right? And so we have to identify the lowest power of each of these things. So let's just write it out. So we've got x to the negative 1/2 times x plus 1 to the positive 1/2 plus x to the positive 1/2 times x plus 1 to the negative 1/2. Remember the power of 1/2 just says that you're taking the square root, right? And then the negative 1/2 just means that it's in the denominator, right? The negative power bumps it down to the denominator. But I'm not going to worry about that right now, but we could if we wanted to. So first thing I'm going to do is I'm going to go ahead and look at each of these. So just like I did before where we had that 7x to the 4y squared something something, I'm going to look at each of these terms, right? Because this x to the negative 1/2 times x plus 1 to the power of something times x plus 1 to the power of something. So I've got these x's times an x plus 1 term, right, on each of these. So I should be able to pull out a common x and a common x plus 1 term. I'm going to focus on the x value first, okay? And so here, I'll make a note. Pull out a common x to the negative 1/2. Okay. So because that's the lowest power, right, or the smallest power. So to do that, I'm going to have x to the negative 1/2 times x plus 1 to the 1/2. That first term stays the same, but what I'm going to do if I want to be able to pull out an x to the negative 1/2 from this next x, what I have to do is I have to kind of extract it, right? So just like we did 14 divided by 7 earlier, right, I have to do the same thing with the x to the 1/2. So what I'm going to do is I'm going to rewrite x to the positive 1/2 as x to the 1/2, or sorry, negative 1/2 plus 1, all in the exponent. Okay. Because I want to pull out this x to the negative 1/2, so I need an x to the negative 1/2, x to the negative 1/2. Now I'll be able to extract that, but we also see that x to the negative 1/2 plus 1 is just x to the positive 1/2, which is where we started here. Right? And then I'm just going to leave that x plus 1 to the negative 1/2 for now. We could do these simultaneously, but I feel like that's too much. So now, this is x to the negative 1/2 times x plus 1 to the 1/2. Oops. Plus x to the negative 1/2 times x, right? Because I'm going to rewrite x to the negative 1/2 plus 1 as x to the negative 1/2 times x, and you should be able to convince yourself that these are equivalent still. Times x plus 1 to the negative 1/2. So now I've got the x to the negative 1/2, x to the negative 1/2. I'll be able to pull that out. So what I'm looking at is x to the negative 1/2. And then just to emphasize it, I'm going to put square brackets. You can use round brackets too if you want, but I like kind of nice square brackets if there's a lot on the inside. I don't want to forget to expand it in if I have to later. So then I've got x to the negative 1/2 times x plus 1 to the 1/2 plus x times x plus 1 to the negative 1/2. Okay. So now I've pulled out this common x to the negative 1/2. I'm going to do the same thing with the x plus 1 to the negative 1/2 because that's my smallest power. So I'll be able to pull that out from the x plus 1 to the 1/2 using that same trick, right? Recognizing that 1/2 you could rewrite as negative 1/2 plus 1. Okay. So now we're going to pull out a common x plus 1 to the negative 1/2.
Okay, so
Do you have a question, Tyler, or should I mute you?
oh no, sorry about that.
Oh, no worries. For some reason, it doesn't put you guys on mute when you come in. I thought I had set it to mute, but anyways, doesn't matter. It's nice to hear some life out there. So if I pull out a common x plus 1 to the negative 1/2, then I've got x to the negative 1/2 I've already pulled out. I'm going to deal with the inside of these brackets here. So x plus 1 to the negative 1/2 plus 1, right? That's the one I need to change, plus x times x plus 1 to the negative 1/2. Okay. Same idea, x to the negative 1/2 times x plus 1 to the negative 1/2 times x plus 1. Plus x times x plus 1 to the negative 1/2. Now I can pull this guy out, x plus 1 to the negative 1/2. I'll clean that up. From both terms. So now I can have x to the negative 1/2 times x plus 1 to the negative 1/2 times x plus 1 plus x, because I've pulled out everything else. But wait, there's more. We're not quite done, right? We can simplify this a little bit further because we've got the same power, right? So by those exponent laws, as long as I treat x plus 1 as one thing, then I can combine these under the negative 1/2 power, right? And so here, let's just make a note. Use exponent laws to combine. So we get x times x plus 1 to the negative 1/2, right? Pulling that negative 1/2 outside. Because I'm multiplying inside, like I said, as long as you treat x plus 1 as one thing, you're allowed to do that. But then also we've got x plus 1 plus x. I can just rewrite that as 2x plus 1, right? So 2x plus 1, just to simplify things a little bit. And even inside here, you can leave it as it is, x times x plus 1, but it might look nicer if you have this expanded out, right? So x squared plus x. So this is x squared plus x times, or to the power of negative 1/2 times 2x plus 1. Now we've factored. Quite a bit of work. You could have, like I said, you could have worked the x's and the x plus 1s simultaneously, if that makes sense. But I like to do it kind of methodically. It's slower, but you don't miss anything. Okay. So now this is this first thing factored, right? So if we were asked to factor this, we should end up like this down here. Okay. So a little bit tricky, but as long as you remember your exponent laws and apply them, then you should be able to pull out common factors even if you've got fractions in those exponents. Let's see here. So we've got all these problems that you can work through. We'll just do one of these. We'll do in theory, the hardest one is the last one. All right, so we'll do that. So we want to factor the expression completely. So what's nice is I'm not seeing any fractions in the powers here. I'm seeing a little bit of a pattern, right? Sort of. So just thinking about those special products. In fact, I'm going to bring those in so we can compare them side by side, which we'll now call the special factoring formulas. Oh, maybe I'll crop. I don't actually need that. I think and I can make it bigger. Okay. So first thing we want to do, so if we're having to factor something like this, kind of a big nasty, right? First thing I want to do is I want to scan this to see if I can match it to anything in here, right? So 126, step 1. See if we can rewrite the expression to look like one of the special factoring formulas. So I'm going to write it out here. And I've got a squared plus 2a squared minus 2 times a squared plus 2a minus 3. Here, I'm going to make a note and say, okay, well, just kind of putting my blinders on a little bit, right? This looks sort of like I've got one term here, a squared plus 2a. If I just treat that as one thing, right? I've got it appearing here again, right? So I've got, let's call this thing a. Then what I've got is I've got a squared minus 2a, right? Because this is a again, right? That's the same thing. I'm going to treat that as one thing. So I've got a squared minus 2a, and then here we kind of lose it a little bit, and it's not obvious where we have to go, right? But if I start and look at what I've got, a squared minus 2a, then, well, a squared minus b squared, that's out, not an option. A squared plus 2ab doesn't really work, but the a squared minus 2a, we're off to a good start, right? And so, and then of course, if we look at the next two, they don't work, right? So this looks a lot like a squared minus 2ab plus b squared. This looks, I'll put it because it doesn't quite, looks like a squared minus 2ab plus b squared, which we can rewrite as a minus b squared. So if we can just figure out what b is here, right, to get this whole thing, then we can easily rewrite it as a minus b squared. Right? Easier said than done, right? Because what I need here is I'm missing a minus 2a. I've got that, but then missing a b, right? And then here, this should be, or it's not really missing, it's there, it's minus 3, but we need minus 3 to look like b squared, right? So there's a trick that we do, right? And we say, okay, well, I can't change this, right? So what I'm gonna do is I'm gonna say, well, I've already got my 2a, so minus 2a, so b must be 1, right? In order for this to stay intact, right? We see that in minus 2ab, b must be 1. Okay. Which means that, okay, we've got a squared plus 2a squared minus 2 times a squared plus 2a minus 3. Okay. This, if a is a squared plus 2a and b is 1, right, then a squared minus 2ab plus b squared will look like a squared plus 2a squared minus 2a squared plus 2a times 1 plus 1 squared. Okay. So the only thing that's different here is I've got -3 when I should have +1. Just like we did with the exponents, right? What if I rewrite -3 as 1 squared minus 4, right? That puts me, that's equivalent to -3. So we rewrite -3 as 1 squared minus 4. I'm allowed to do that. It's true, 1 squared is just 1. 1 minus 4 is -3. So I can replace that -3 with 1 squared minus 4. So now we have a squared plus 2a squared minus 2 times a squared plus 2a plus 1/2 minus 4. That's the same as plus -3, so -3. Now I'm going to rearrange this thing and have it look like, so this becomes, in square brackets, I'm going to have this a squared minus 2ab plus b squared. So I've got a squared plus 2a squared minus 2a squared plus 2a plus 1 squared minus 4. Rearranging the brackets. In fact, I didn't really need brackets around here, right? It would just be plus 1 squared minus 4. But I wanted to show that it was from the same term, -3, right? But I'm allowed to do this, right, where I can group these together and then have the -4 on the outside. So this, this we can rewrite as a minus b squared, where a is the a squared plus 2a and b is just 1. So this becomes a squared plus 2a minus b, which is 1 squared, and then minus 4. Oops, do it in blue so it's So, okay, a squared plus 2a minus 1 all squared. There's nothing really I can do here. I've still got the square on the outside. I can get rid of these brackets, right? A squared plus 2a minus 1 and then all squared, but then remembering that we've got this minus 4 on the outside. So this becomes a squared plus 2a minus 1 squared minus 4. This is now factored completely, right? I can't kind of accordion it up any tighter, right? And so then we say it's factored completely. This is now factored completely. So that's a trick that you want to keep in mind, right? Is even if it doesn't look like a perfect square, potentially, right from the get-go, if you can manipulate it to look like a perfect square, right? If you can rewrite -3 to kind of help you get to that perfect square, then that's good, right? Because then you'll be able to use the special factoring formulas in order to factor this to something nice and compact. Do you need the square? Do you mean this one? Like this square here? Okay, cool. Sounds like it's under control. So what I'll do, I'll make sure that I post the solutions. I have some of the solutions, so I have to figure out the rest of them, but I'll post the solutions to a lot of these, and then you'll be able to check your work, right? But definitely go through and see what you can do on your own. But then I always like to give you the solutions to work from too. Right? Sometimes it's easier, especially I learn better by kind of working from the solution, because I can easily convince myself of something that's wrong, and then just kind of work down a rabbit hole. So sometimes I'll work through a problem on my own, and then I'll check it against the solutions. If it's right, then that's great. What a good feeling. And if it's wrong, then I'll kind of work backwards instead. Right? So I know that that's what people do, so that's why I always post the solutions, but I just need to find them first for you guys. Okay. Let's see here. So we can also factor by grouping terms. It's a little bit easier, but let's just do one way easier than what we just did. I guess in a way it's similar to what we just did, but I feel like it's easier. Okay, so for example, if you have polynomials with at least 4 terms, so that's kind of tricky. So with at least, with at least 4 terms, so that's a big polynomial. If you have to factor something big like that, one thing to try first is to maybe try grouping the terms to make them look like a smaller polynomial. For example, if you have x to the 3 plus x squared plus 4x plus 4, right, what you can do is, well, I've got 4 and 4 here, so I can lump those together, and then I've got x to the 3 plus x squared. So just using brackets, I'm able to kind of manipulate this. Notice that I haven't changed anything. I've just put brackets around these things. And then what I'm able to do is I'm able to pull out a common x squared and pull out a common 4, right? And then what I'm doing is I'm pulling out, okay, an x squared and a 4 because I've got this common x plus 1, right? So now I've got x plus 1 that I'm pulling out as a common factor, and then I'm left with x squared plus 4 times x plus 1. So that's kind of nice. Let's do, I don't know which one. I'm trying to pick one. Let's try 86. How come the numbers are weird? Jumped around. 86 is 3x to the 3 minus x squared plus 6x minus 2. So what I'm going to do is I'm going to try using the same kind of method that I used up here, right? So I've got 3x to the 3 and then x squared. It looks like I'll be able to pull out a common x squared, right? Another option would be, well, if I group the 3x to the 3 and the 6x, I'll be able to pull out a common 3x, which might also be useful. So I've got a couple of options here. I'm going to try this first way, and then if that doesn't give me something easy to look at, then I'll try the other way. So this becomes 3x to the 3 minus x squared plus 6x minus 2. So from the 3x to the 3 minus x squared, I can pull out a common x squared and be left with 3x minus 1. From 6x minus 2, I can pull out a common 2. So I've got 2 times 3x minus 1. Convenient. Right? These are now common factors. So what I end up having is I've got x squared plus 2, right? Pulling out the x squared and 2, and then I've got a common factor of 3x minus 1. We can try it another way too. I haven't worked through it, so let's see how it goes. It might put me, no, it'll put me a little bit different. So no, it'll put me at the same place, but let's just try it a different way to show you that there's kind of multiple ways to go about it. Or if we have 3x to the 3 minus x squared plus 6x minus 2, I can rewrite it as 3x to the 3 plus 6x, right? Rearranging that way. Now I've got minus x squared minus 2. Actually, I'm going to ditch the brackets for just a little bit here. Minus x squared minus 2. And then 3x to the 3 plus 6x in brackets. And then when I put brackets around here, you know what I'm going to do? I'm just going to pull out that negative. I've got a negative out front here on both of these. So I'm safe to go minus x squared plus 2. Right? Just being careful with that negative. So from this first chunk, I can pull out a common 3x. I can pull out a 3 at maximum from the coefficients, and I can pull out an x at maximum from the variables. So I've got a common 3x, and then whatever's left over from 3x to the 3 is x squared plus 2 minus x squared plus 2. Notice that we're back to x squared plus 2 as my common factor. So now I can mix it up. I can say, okay, I'm going to pull out this x squared plus 2 as my common factor, and then be left with 3x minus 1, right? Minus 1, because here, if I've got minus, then I've got technically minus 1 here as a coefficient, which is the exact same thing that we landed on here. So play around with it, see what you can kind of see, what kind of groupings you like to work with. And that's good. Okay. Crazy. We've got time to get into 1.4. Not much, but a little bit. Are there any questions though? So factoring, definitely going to need some attention, right? Quite a bit of work involved, but like a lot of math, if you've seen enough of them, you'll start to recognize these patterns and say, oh, I've done something like this before, and that time I did this, and then you can just kind of try it from there. Okay. I haven't seen any questions. So let's get into rational expressions then. Oops, I copied that's okay. So a quotient is just a fraction, right? And so a quotient of two algebraic expressions is called a fractional expression, right? So like I said, a fraction. So if we've got an algebraic expression is just anything that we've seen that's more than just a number, right? So 2x or y squared plus 4 or x to the 3 minus x or the root of x squared plus 1. These are all algebraic expressions. Okay? And so a quotient of these two is called a fractional expression. So a rational expression is a fractional expression where the numerator and the denominator are polynomials. So these are the ones that we're going to be dealing with. Okay? Polynomials, remember, just have the different powers of x in your denominator, or sorry, in your terms. So something like 2x, that's a polynomial, x minus 1, that's a polynomial, y minus 2 is a polynomial, y squared plus 4 is a polynomial. Each of these are polynomials. The only one that's not a polynomial is the root of x squared plus 1, just because we can't have the root in there. Inside the root is a polynomial, right? But the square root of x squared plus 1 itself is not a polynomial. Okay. And so just something to keep in mind. Okay. Just as a reminder, we've talked about it before, right? But if we've got a fraction is the numerator over the denominator. Okay. So one thing, if we're dealing with expressions like these, right, fractional expressions, so anything where we have variables up top and in the bottom, or just one of these places, we're going to have to deal with the domain of the expression. Okay? So the domain is essentially all the values that we're allowed to have. So what we say is that the domain is just all the values of x that are allowed in the expression. All the values of x, right, or inputs allowed in the expression. Which means that we need to remember some of these rules that we've outlined earlier, right? But we've summarized them here. So here, in fact, I'm just gonna copy and paste it bigger. Okay. All the things that we need to keep in mind for now. We're going to add some things later on, but for now, we know we can't divide by 0, right? So if we've got something in the denominator, right, so something in the bottom, it can't equal 0 because that's illegal math. So here is essentially a list of illegal math. So things we need to avoid and things we need to avoid in our domain. So if we've got the root of x, so this is just the square root of x. Remember, we can't take the even root of a negative number. So if we've got, especially if we've got the square root of x, then x has to be larger than 0. It can equal 0. The square root of 0 is 0, so that's allowed. Okay? However, if you've got the combination of the two, right, 1 over root x, well, root x is going to be positive, right? And one of the conditions on root x is that x has to be greater than or equal to 0, so that's fine. But also joining with that is that we can't divide by 0, right? And so the root of x is not allowed to be 0 anymore. But the only way that happens is if x is equal to 0. So then we have this kind of morphed constraint of x has to be greater than 0, so it can't be equal to 0 if you've got root x in the bottom, in the denominator. So here, this first one says that we can't divide by 0. Right? If there are values of x or any inputs that give you division by 0, they have to get pulled out of the domain. We can't take the square root of a negative number. We can't take the square root of a negative number. And here, right, this is a combination of the two. Combination of the two above. So these are just things that we need to drill into our minds, right? We can't divide by 0. I can't take the square root of a negative number. And there can be combinations of these things that I need to keep track of, right? And kind of the overlap of all those conditions, that's going to be your domain. Okay? So your overlap or your domain will be the overlap of all the conditions. Okay? So what I mean by that, we'll do an example. we'll do 14 because it's got a combination of all these things. But let's just talk about these other ones first. So for 7, things I'm looking out for, I'm not dividing anything, so okay, that's all right. There's no constraints on it yet. I don't have a square root, right? And so here, the domain would be just any number, so the set of real numbers. Well, let's just do, okay, fine. Let's just do 7. 7, there's no division and no roots. So we have no constraints. So the domain, and I'm going to use set notation, set builder notation, is the set of x's such that x is in the set of real numbers. Do you guys remember that? That was from way back, beginning of the course. This is the set of x such that, right, x is in the set of real numbers. Right, which is just any number that you can think of is allowed. Okay. Scanning number 8, same thing, no division, there's no roots, so I can have x in the set of real numbers. Number 9, x squared minus 1, there's no conditions here, but I am dividing, so I need to make sure that x minus 3 does not equal 0, which means that x cannot be 3, right? Let's do this one. Number 9, x squared minus 1 over x minus 3, right? One thing to keep in mind is that x minus 3 cannot be 0. I can do math around these inequalities, which means that x cannot be equal to 3, right? I add 3 to both sides. So the domain is the set of all x's such that x is not equal to 3. Hmm. 10, very similar, right? There's no square roots, but there is a fraction, so I need to make sure that 3t plus 6 does not equal 0. But I do the same thing that I just did here, except I would replace it with 3t minus 6 cannot be 0, and manipulate it to figure out what the condition is on t, and that's my domain. For 11, right, I do have a square root. I don't have a fraction anymore, so I've got a square root. So in the square root, I know I can only have positive numbers or 0. So x plus 3 has to be greater than or equal to 0. So let's see here. 11, the root of x plus 3 in the square root, x plus 3 has to be greater than or equal to 0. It's allowed to equal 0 because it's just the root on its own. So then x must be greater than or equal to -3. We'll deal more with inequalities later, but the only time that that you can't just treat the greater than or equal to or less than or equal to sign as just an equal sign is if you're dividing by or multiplying by negative numbers. Okay, so here it's totally fine. And like I said, we'll come back to that when it's important. So here, number 12, 1 over the square root of x minus 1. So I've got a condition on the x minus 1, right? It can't be negative, but also I can't have the square root of x minus 1 equaling 0, because then I'm dividing by 0, right? So hey, I was just going to go and do 14 and be done with it, but let's do 12. Let's get over of x1 to hopefully her condition is x such that, and then the condition in there. So not too bad. So the domain here for the previous one is x such that x is greater than or equal to -3. Here, right, can't divide by 0. But also can't take square root of a negative. So what that means is that the root of x minus 1 has to be greater than or not equal to 0. Right? Because we can't divide by 0. So the condition then is going to be, like I said, we can manipulate this inequality by just squaring. So just like we would with an equal sign, so we get x minus 1 is greater than or equal to 0 squared. 0 squared is just 0, which means that x must be greater than or equal to 1. 0 plus 1. And if we just check it, if we let x be 2, 2 minus 1 is 1. The square root of 1 is allowed, right? Whereas if you go on the opposite side, so x has to be greater than 1, but if I did x is 0, right, then I've got 0 minus 1. I'm taking the square root of a negative number, which is not allowed. So it checks out. So the domain here is the set of x's such that x is greater than 1. Now, the reason I want to do 14 is because I want to show you we can have multiple conditions that we need to satisfy, right? And so, of course, that's only going to happen if we take the overlap of the two. So if we look at 14, 14 is the square root of 2x over x plus 1. So I've got the square root of 2x over x plus 1. Here, I'm going to say 2x has to be greater than or equal to 0, right? I have to take a square root of a positive number, or 0, right? So it can't be negative, but 2x has to be greater than or equal to 0. Okay. Down here in the denominator, I can't divide by 0, right? So what that means is that x plus 1 cannot equal 0. Okay, solving just in terms of x here, if 2x has to be greater than or equal to 0, then I can divide both sides by 2 and just say that, okay, well that means that x has to be greater than or equal to 0 divided by 2. 0 divided by 2 is just 0. Okay. So, and then for the denominator, this is saying that, well, if x plus 1 can't equal 0, then x can't be -1. So now we're going to exercise our number lines. I find number lines to be more useful if we're looking at things and we're trying to find the overlap, right? If you just look at these and you see where the overlap is, then that's great. But for me, I need a little bit more visual, so I'm going to do a number line here of all my x's, right? So here are all my x's, and I've got some reference points, right? I'm at 0. I've got points at -1, and those are the only two I've pointed out here. Depending on the question, you might want to put some other reference points on here. Maybe it's nice to have 1 to show that it's going in the positive direction, even though it should be implied and understood. So if I do my light blue domain, right, x has to be greater than or equal to 0. So greater than or equal to 0, oops. I've got a closed dot at 0, and then it just keeps going, going, going in the positive direction. Okay. So that's my domain for the numerator, essentially. And x has to be greater than or equal to 0. If I do my domain of x can't be -1 for the green, right? Everything's allowed here except at -1. Okay. So now, looking at this, the overall domain is going to be where there's overlap, right? So from 0, including 0, everything's a go to the right, right? Moving in the positive direction. Okay. So here, this is the domain equals the overlap. Okay. So what that means is that the overall domain is the set of x's such that x is greater than or equal to 0. All right. I think that's good for today, but definitely go through and practice the factoring and the domains because they can be a little bit tricky, a little tedious. Yeah. Are there any questions? Yep, just gotta practice. Practice, practice, practice. So there are these extra questions here that I'll put the solutions up for. So I would work through those problems first. So all the ones in the handouts, right? Especially for factoring and for the domain. I mean, we kind of did those little guys here, but it won't hurt to just work through them again. I don't have any video solutions except for obviously the ones we worked through together. So it's just the answers. I think some of them might have kind of worked out solutions, so not just the answer, but all the work in between. But I can't remember. But yeah. Okay. Good. I am going to stop this recording. Stop.